Okay, so last thing we're going to finish up with today is section 5.3. Okay, we've talked about how to write complex numbers in polar. Okay, just as a reminder of what a complex number in polar looks like, r cosine theta plus I sine theta. The way you find r and the way you find theta is exactly the same way you find them with real numbers. You don't do anything different with imaginary. And the real advantage to writing complex numbers in polar is that it gives you a quick way to do multiplication and division. So I've already told you, but all the stuff about foiling and conjugates and I-squareds and combining like terms, all of that, all goes away. Okay, we don't have to worry about any of it if we use the polar form. So I'm going to show you what the formula is, and then we'll go through and use it. Okay, so I'm going to write two complex numbers in polar, okay, just generically. When I give you a real problem, it'll be set up more like, let's see if I can just find something with numbers on it. A real problem will be set up like that. Okay? I'll give you a number for r, and I'll give you a value for the angle. All right. So for my first complex number, I'm going to let the radius be r1, and I'll let the angle be theta 1. For my second complex number, for now, we'll just call the radius r2. We'll call the angle theta 2. Okay. If you want to take those two complex numbers and multiply them together, okay, I've called them z1 and z2. You could call them complex number 1, complex number 2. You can call them whatever you want. Okay? But if you want to multiply them together, here is the formula for how to do it. There's two things you have to do. First thing you have to do is take r1, take r2, and multiply them together. Very easy calculation. You can use your calculator if they're big numbers, but most of the time they're not that big. So you take r1 and r2, multiply them together. The second step, and the last step, is to take theta 1, theta 2, and add them up. So your new radius is the product of each of the original ones, and your new angle is the sum of the original angles. And that's it. So just by taking two numbers and multiplying them together, taking two numbers and adding them together, we have replaced everything that we learned yesterday about conjugates and everything I keep saying. Okay, all that stuff goes away. That's all you have to do. But the trick is it relies on your problems being in polar. Okay, so you have to be given information in polar. If you gave me the information the old way, it would be more work to change it to polar and use this method, I think. I would just go with all the foiling and the conjugate stuff. Okay. So, but the problem I'm going to give you is already in polar. So it's set up perfect to use this shortcut. Okay, so my first complex number is 3, has a radius of 3, and an angle of 20. So it's 3 cosine 20, I sine 20. And my second complex number has a radius of 5 and an angle of 100. Okay, so somebody's already done the work that we did in last night's homework. They found the radius using Pythagorean theorem. They found the angle using the inverse tangent. Now they want us to multiply them together. Let's start with our radius. When I multiply these together, how about radii? what is my radius going to be? 3 times 5. Yeah. Take the first radius times the second one. And what does that come out to? 15. So all that takes the place of having to do Pythagorean theorem. That's your new radius. You don't have to worry about any of that other stuff. Last thing I need is my angle. So Abby, how do I find my new angle?
You add the 120.
I just take the two angles that I have and add them together. And what do you get? 120. Yep. And that's how you multiply two complex numbers in polar. And that's it. That's the final answer. Okay, so you don't have to worry about all the stuff that happened yesterday, especially the I squared. Some people forget to change that to -1. That's something that comes up a lot. Any questions on how we multiply those? Yep.
Can you explain what this represents?
Z is just what I'm calling the first complex number, and W is what I'm calling the second one.
Okay, so there's no like.
It's just the name. You could call them anything you want. You could call them, R and Q or whatever you want to call them. So my first complex number was called Z. My second one was called W, and I want you to multiply them together. Okay, let's try this one. We've got 1/2 cosine 15, I sine 15. So radius is 1/2, the angle is 15. And the second one, the radius is 10, and the angle is -30. Okay, I put, anytime that I have a negative argument to a sine or a cosine function, I always put it in parentheses, because I think this looks confusing. To me, that looks like cosine -30, but it's really the cosine of -30. -30 is being plugged into the cosine function. Okay. Colby, what would my radius be here?
5.
Yep. R1 is 1/2. R2 is 10. Multiply them together, we get 5. Okay. Ethan, what about my angle?
-30.
All right. How'd you get that? So remember, the angle we're going to write here is a combination of the two up above it. Do you remember what we do with each one of them?
Yeah. -15.
-15. How'd you get that?
Adding 15 to -30.
You add the 15 to the -30. Yep. So we get 5 cosine -15 plus I sine -15. Okay. Now, let's rewrite that so we don't have a negative angle. Can someone tell me what -15 is the same as? Yeah. Go ahead.
345.
345. So one way to fix this, to get rid of the negative angle, is to add 360 and get 345. That's one way. Okay, the second way to fix that. Okay, I'm going to show you something on the calculator and see if you notice a pattern. Okay, let's take any angle, it doesn't matter. Let's take the cosine of 27. Okay, that's what you get. The value you get isn't important. I want you to compare it to the next value. That's important. Let's do the cosine of -27. What's the difference between those two answers? There isn't. So what ends up happening is if you have a negative with a cosine, it actually doesn't even make a difference. You can just get rid of it. You don't even need it. So the cosine of -15, cosine of +15, same thing. Okay, so let's start with that. Let's try it with sine. Let's see if the negative makes a difference there. Let's do the sine of 27. Okay, that's what you get. Let's do the sine of negative 27. Did we get the same answer?
Oh, yeah. No. Oh. Can't see that very well.
Oops.
That's a couple times. They're not the same, Mr. Hager.
They're not the same, right? They're kind of close. Well, I guess it depends on how you think of close. But what are they, basically? How are they related? Not the same. They're opposites. Yeah, they're opposites. So positive 0.45, negative 0.45. So what you can do is the negative makes a difference. But what you can do with a negative is you can put it in front. And what I'm trying to show you is that if you have the negative inside or you move it to the front, you get the same answer. Okay? So with a negative on the sign, you can move it in front. So let's do that here. I need to
Is
get
your
rid of that.
calculator on the screen?
What's that?
Your calculator, like the screen part of the calculator, can you like type it in there?
Can I type it in?
No, like on the screen part, is that touch screen? Like can you move the cursor thing?
No.
No.
No, I
How'd you
can't.
get it to how'd you get it to zoom out like that?
Oh, I can drag it over here. And now it's a picture. Yeah, it's technology stuff.
Yeah.
Way past the model.
Mr. Hager,
Yes.
do you happen to know how to do this, or can you just add 360 degrees to it and call it there?
You should be able to just add them.
You should know both ways in case it's a matching question and you
Right.
don't see the answer that you just said, adding 360. So I think the second way that I showed you, although it's different, I actually think the second way is easier because you don't have to do any arithmetic in your head at all. You just take the negative from the cosine and get rid of it. And you just take the negative from the sine and put it in front. Just like we did here. Took the negative from the 27, we stuck it in front, and we saw that it comes out exactly the same. Okay? So now you know two ways. Did I move something? Yeah. Now you know two ways to get rid of the negative. One way is to add 360. The second way is right there. We'll probably try that one more time. Okay, but that's all I was going to do for multiplication. So any questions on how to multiply two complex numbers in polar? Just multiply the radii, add the angles, you're done. Okay, let's look at division. All right, so to do division, I'm going to set it up the same setup. First complex number has a radius and an angle. I'm going to call it R1 and theta 1. The second complex number also has a radius and an angle. We'll call it my second radius and my second theta. And now, if you know how to multiply in polar, what you would think the formula should be for dividing is what you would think would happen. Okay, it's very similar to the other one. So to divide these, to find the quotient, what do you think I'm going to do with R1 and R2? This time, keeping in mind what we did the first time. We're going to divide them. So we're going to take R1 and R2. We're going to divide them. What do you think I'm going to do with theta 1 and theta 2? Subtract them. Okay. So to divide, these two steps are going to take the place of finding a conjugate, foiling, changing I squareds to -1, combining like terms, and separating it into two parts. All you have to do is divide radii, subtract angles, and you're done. But again, the trick, why is this so easy? Well, because you have to start with numbers that are already in polar. If they're not in polar to start, it's more work to change them to polar. But the problem I'm going to give you right now, it's already in polar, so it's ready to go. Okay. So there's our problem.
Can you scroll up a little bit?
Okay, so I've called the two complex numbers z and w. Again, you can call them whatever you want, but the point is you're just going to divide them. And now we have to be careful with division because look at what we have right here. That's subtraction. When you subtract, does the order make a difference? Yes, you can't switch the order. So you have to make sure you subtract in the correct order. How do you know the correct order? It's always the top one minus the bottom one. First minus second. Right? So in this case, whatever the angle is for z minus whatever the angle is for w. All right, so let's do this out. Right, how about Sam? Can you tell me what my radius would be?
3 divided by 5.
Yep, and we just leave it like that. 3/5. Okay. So there's your radius. Cosine. And Jamaica, what would my angle be?
The cosine would be, I'll say 45.
45, yep. Take 75 minus 30, and you're done. Okay, so that's one where you don't have to worry about a negative on the angle, and there'll probably be some on the test that you don't have to worry about negatives either. But there might be a negative that comes up sometimes. Okay. Questions on that one? Okay, so we'll try one more with division, and then we'll do the last thing, which is about the same difficulty as these two things. So I have z divided by w. Okay, so I've written out z and w. What's my radius going to be here when I take z and divide it by w? Yeah?
5.
Okay, be careful. So if this was a 2, then 10 divided by 2 would be 5. 20, right? This is 10 divided by a half, which is 20. It's a little tricky, but a lot of people look quick and make that mistake. And what about my angle? Don't worry if it comes out negative, just leave it for now. About Liz?
Cosine -80.
Negative 80. All right, so cosine negative 80 plus I sine negative 80. All right, can somebody give me one way that I can fix that so I don't have a negative? And I don't care which way you do it. Yep.
Get rid of the negatives from the first 80, then change the plus in between that and I sine to negative.
Yes. Question? Caitlin? Question? Okay. So, as Alan just said, get rid of the negative on the first 80. And then on the second one, you can't get rid of it, but you can then just move it to the front. Perfect. That's a good way to do it. What's the other way you could do it if you didn't want to do the negative moving and thing?
You could just add 360.
You could just add 360 to negative 80. I'm not going to write it down, but you could. Okay. So any questions on dividing? So doing it in polar, it saves you a little bit of time, okay, for multiplication and division. But the next thing in polar saves you way more time than either one of these. Okay, polar is way, way, way better. Okay. And let's look at an example of something, and then I'll show you what the theorem is. Put 2 plus 3i squared. Okay, I wrote it the old way. That's rectangular form. What does that mean to do? 2 plus 3i with a 2 up higher. Okay, what does square mean? Like if you had to explain it to someone that never saw exponents like this before.
Multiply it to itself.
Yeah, you take what's below and multiply by itself that many times. So this means 2 plus 3i times 2 plus 3i. And then if we wanted to do that out the old way, we have to FOIL it. So we get 4 plus 6i plus another 6i. And then I have 3i times 3i, which is 9i squared. Or what number is 9i squared? Negative 9. And I'm still not done. I have to combine like terms. 4 minus 9 gives me negative 5. Now, if I wasn't talking as I went through that, I could probably do that in maybe 10 seconds or so. Just FOIL it real quick, combine like terms without saying anything. Now, if you wanted me to do this, that means I have to write out 8 copies of 2 plus 3i and FOIL each one of them one at a time. So I would have to do the first 2, and I already know what that comes out to. And then I would take that answer, multiply it by the next 2 plus 3i, do it again, and again, and again, and again. I'd have to do it 8 times. Little time consuming, but I could do it. It'd probably take me maybe 3 or 4 minutes to do all that out carefully. Now, if you gave me something like this, now it's not even reasonable. I couldn't do that if I had all day. It's just way too many steps. So rectangular, raising numbers to powers in rectangular is okay if the power is really small, maybe even up to 5 or 6. But if the power just gets ridiculously big, this is an awful way. FOIL is not a good way to do this. So that's where this comes in. This theorem allows you to raise a complex number to any power you want. And whether you tell me to do the second power or the 2 millionth power, I can do either problem in the same amount of time. Doesn't matter what the exponent is. But the trick, how do you think our complex number has to be written? How has it had to have been written for the other 2 formulas?
Rectangular.
Well, rectangular is the old way. So this has to be written in polar. Okay? You have to use polar with this theorem. So the trick to raise a complex number to a power, it's about the same difficulty as the other 2 tricks. The first thing you do is take your radius and raise it to the power. That's the first step. So in an actual problem, they'll give you a radius, and they'll tell you the power they want you to use. Okay? So take your radius, raise it to the power, take your angle, and multiply it by the power. And that takes the place of all the foiling you would have to do, which could get pretty bad if the exponent was high enough. Now, if you just asked me to square something, would I use this formula? Probably not, because I can FOIL something pretty quick. But if you ask me to raise something to like even the 15th power, which isn't that big, but it's big enough, I would use this formula. Even if you gave me something like this, and you said raise this to the 15th power, I would take the time to convert that to polar and then use this theorem that I just showed you. Okay. It's going to take probably 60 seconds to change it to polar. It's probably going to take me another 30 seconds to plug it into this formula and do it, but I could still do the whole thing in easily under 2 minutes. If you want me to raise this to the 15th power without using the trick I just showed you, it's probably going to take me probably 10 or 12 minutes to do it. It's going to take me quite a long time. So that's the 2 steps. Raise the radius to the power, multiply the angle by the power. All right, so let's try this one. Okay, it looks like I don't have a problem, so I'll just make one up. We've got 3 cosine 20 plus I sine 20. So that's the original problem. And I want you to raise that to the 8th power. This is already in polar, so that's great. It makes using this theorem very simple. Okay, I'm not sure if I actually said the name of that theorem, but that's French. We pronounce, does anyone know how to pronounce that? De Moivre. You say De Moivre's theorem, not De Moivre's. We don't say that. It's De Moivre's theorem.
Is it a guy?
I honestly don't know if it's a guy or a woman. I don't know. It's probably in the book. I'd have to find it. Okay, so we want to raise that number to the 8th power. Okay. You don't have to tell me the answer, but can someone just tell me the calculation first for the radius? How would I get my new radius? Yep, Lauren?
3 to the power of 8.
3 to the 8th power. Okay, I'll do that on the calculator in a second. And how about the calculation for my angle? Yep.
Is it 8 times 20?
It's the angle times the power. 8 times 20, which is 160. And that's it. That's the final answer.
So we don't have to solve the 3 to the 8th power?
Well, the 3 to the 8th, it depends on how big it is. If it gets ridiculously big, like if it's in the millions or billions, we're not going to do it out. I mean, 3 to the 8th is kind of big, but I don't think it's not super big. So if you wanted to do that one out, you could. I would say anything that's like in the thousands, you could do out. If it starts to get into the millions or billions, we just leave it. Okay? But honestly, even if you just left that one, that would be okay. Because it's big enough that we can't do it in our head, but it's not super big. Okay. And that's it. Any questions on De Moivre's theorem? Okay, so 3 very nice formulas to multiply, divide, and raise to a power, as long as you're okay with using polar. All right, so the homework, just a few questions on 333. It's 33 to 37 odd, 41 and 42. Make sure you do not follow the directions in the book for 41 and 42. They tell you to change your answer to something else. I'm telling you to just leave it in polar. Okay, so tomorrow we'll have our second test for the term. If you haven't made up the first test, make sure you get that done before tomorrow. And remember that I'm not after school for extra help today. I'm going to be back on Thursday starting next week. But this was my last week. I stayed yesterday.